First of all, regarding your PS4, I've checked your PS4 assignments and so far you all did very great. But then there was one thing that I have to emphasize, that is regarding the runtime. Okay, most of you guys use recursion. That is why in every time you call enumerate nodes, okay, you go to the left subtree, you go to the right subtree, and then you count how many nodes in the left and right subtree. Count nodes itself is on time. If you recurse in left and right, then there will be on over 2 plus on over 2. That will give you on. Repeat until how many levels, that is n of n time. Unfortunately, there's actually a high penalty for solutions less than on, which is why I have to emphasize this to you guys, okay? So from now on, try to think of better solutions instead of just trying to think of the first thing that came to your mind, okay? Especially for, I think one of the common mistakes is for problem 1C. A lot of you try to create new arrays, okay, using arrays.copy or system.arrayCopy, okay? And creating new arrays itself is on time, just for the array creation. Okay? On time, but then you recurse left and right, it becomes something like merge sort. Hence, there will be on log n time. So for this question, one of the best ways to implement is using the 2 pointers. So you'll just use the common array, and then you're going to put pointers there, the start and the end. So some sort like binary search. Okay? Instead of creating new arrays, just have the pointers to point at specific parts of that array. So you're not going to create new arrays every time. Okay? Any questions on PS4? Okay? If no questions, we'll move on to a quick recap. Okay? But in the interest of time, I will not do too much of a recap. So I'm just gonna recap the rebalancing of AVL trees, which I find quite interesting. Okay, but before that, I'll ask y'all a very quick question. If I have a tree with height h, can y'all tell me what is the most number of nodes this tree can have? Or let's do a very quick one. How about h is equal to 3? What is the greatest number of nodes this tree can have?
2 raised to h minus 1.
2 raised to h minus 1, okay. Any other answers? Who agrees it's 2 raised to h minus 1? Okay.
It's binary, right?
It's binary, yeah, binary. Yeah, good catch, yeah. Binary tree, height balance, binary tree. Okay.
2 height balance. Then it's 2 raised to h by 2. As in at least.
Most number of nodes, yeah. Most number. Okay, most number of nodes. So I think height balance will not affect if you are going to talk about most number of nodes. Why is it 2 raised to h minus 1? Anyone? Fatty?
It's basically like you can just do induction.
Okay.
or maybe like the first level it's like 1, and then the second level 2 to the power of 1, and then 2 to the power of 2, until 2 to the power of h minus 1.
Okay.
And if you sum it up, it's like 2 to the power of h minus 1.
Okay, so this is very mathematical. You try to see patterns, then you try to prove by induction that it is correct. Okay, that's actually a way. But here I'm going to show a bit more of a way to find the 2h minus 1 itself. So given that I have a tree with 3 levels here, the height is 3. So this will be height 1, height 2, height 3, right? In this case, this is the maximum number of nodes I can have for a binary tree, okay, as what Freddie mentioned. So I can say this, the number of nodes here is 1 plus 2 plus 2 times 2 again. Okay, so 1 plus 2 plus 4. If I have 4 levels, that means I plus 8. 4 times 2, then times 2 all the way. So this thing, it forms a geometric progression. Okay, 1 plus 2 plus 4 plus 8 plus 16 plus 32 and so on and so forth. This is the maximum number of nodes you can have with a certain height h. Okay, so from 0, 1, 2, 3 until h minus 1, I have a total of h elements here. Okay, because 0 plus 1 plus 2 plus 3. So this will be h elements. Starting from 1, I multiply by 2. So I plug in the formula here. 1 times 2 raised to h minus 1 over 2 minus 1. That will give you your 2 raised to h minus 1. Okay, so this is a use of high school mathematics, okay? Just high school math here. Any questions? Nope? Okay. So that will give us the 2 raised to h minus 1. What about the least number of nodes? We are going to see it in our tutorial question. Okay. Now let's talk about AVL trees. AVL is not some cool name, it's just people's name being smooshed together. 3%. Okay. AVL trees are self-balancing trees. That means we are going to always maintain the height balance property. Can anyone tell me what height balance means? What is height balance? What does it mean for a tree to be height balanced?
The difference between the left and right subtree must be less than 1.
Okay, the difference must be
Less than 2, sorry.
less than 2, okay? Less than equal to 1. Okay? Must be less than 2, that means the difference can only be a maximum of 1 or they're the same. Okay, either 0 or 1, that is height balance. If anything greater than 1, then it's no longer height balance. Okay, it should work for every node in your tree. As long as there is one node that is not height balanced, the tree is no longer height balanced. Okay? Whenever there is a difference in height that is greater than 1, we need rebalancing for us to maintain the height balance property. Okay? So, given this case, okay, lecture case. Suppose I have a node A, the left subtree will go to B, who has another subtree, then this one is the right one. Okay? Left, middle, right. So given that the height of L is equal to M, is equal to K, and then right here is K minus 1, can anyone tell me, is this height balanced or not? Who says this is height balanced? Who says this is not? Okay, so this one is K, but because we add with another node here, that will become K plus 1. Then here is K minus 1. So this is no longer height balanced. It is heavy on the left subtree of A. So how do we balance this up? Right rotation with who? Okay. Anyone doesn't know how to do right rotation? I was still confused with right rotation. If I right rotate this, what do I do first? What do I do? That's the question. What do I do in a right rotation? You all know that it's right rotation, but how to do it? So, suppose I have a hand here, okay? Suppose my hand is holding this. What I'm going to do first is that I want to pull B so that it will become the top of your root. Okay, I'll try to pull B so that it becomes on top. Now what happens here? When B becomes on top, it is a binary tree, right? So it cannot hold 3 children. So what to do next? One of them should be given up. Which one should we give up? The A or the M? The M. Why not the A? Because that will be disjoint, okay? Because you will separate them. So I need to cut off M. If I cut this off, where should I put the M? To the left subtree of A. So that will be your rebalancing. Okay? And now this is already a balanced tree. Because your left subtree, height K, right subtree, height K plus 1. Any questions? No? Okay. Now what about the case where your middle is of size K, but your left is now K minus 1? Is this balanced? This will be similar to the previous example. This one is K, this one is K plus 1, but here is K minus 1. So from root A, this is not balanced. Okay? What should we do now? What should we do now? Okay, common intuition, I'll just write rotate things, I'll just write rotate things, okay? So I'll put the B on top and then the A here. But what happens now is, sorry. Oh, this one is K minus 1, sorry, I forgot. This one is K minus 1, but this part is K plus 1. So it is still not balanced. It is right heavy. So how do we solve this type of problem? Any ideas? Rotate twice. What do I rotate first? so I'll just go through again. This thing, if I directly right rotate things, it happens to be too heavy on the right. Okay? So what I can do now if I'm faced with this question, this part is right heavy, right? Then if I just rotate this, then it will be another right heavy part. So what if I make this left heavy first, then I rotate? Would that be possible? Okay, so how do I make this left heavy? Let's assume that M here has a node, and the node has the children again, okay? So let's assume I have M1 and M2 connected to a node C. This is your M. Okay? What I'm going to do now is I'm going to left rotate everything here. If I left rotate this, okay, just normal algorithm here, reconnect, and now this becomes your left subtree. Okay? Now your left subtree is left heavy or right heavy? Left heavy. Okay, because here it is K, but here it is K minus 1. Okay, so your left subtree is now left heavy. What do I do next? I right rotate in the root node. So when I right rotate, which node becomes my root now? If I'm going to right rotate everything. C. Okay? When I right rotate everything here, my root is A, right? So if I right rotate, I will go to my predecessor. So that will be C will become the root, A will fall down as the successor. Okay? If I right rotate this, I pull C, I take it as my root node. And when C becomes the root node, I have to give up one of the children. Which one do I give up? M2. Okay? So I will give up M2, I connect it to the successor of C, that is A. Okay, I connect it to the left subtree of the successor of C, and now this is already my balance tree. Any questions? Clear? Okay, because this is very important, it will come up in your midterms. Okay, I will emphasize it will come up in the midterms. I've seen it from the past 2 years. Okay, any questions? Yeah, this will be balanced. So just a quick recap on AVL trees. Given that I have a left heavy tree A with the following structure, if B has subtrees of equal height, what do I do? I will right rotate the entire tree. Okay. Now what if B is left heavy?
Rotate once.
I'll just right rotate everything again. Okay. As the lecture mentioned, if it's left heavy, then I can just do the same thing. It will not affect. But what if B is right heavy? Then it happens using the second algorithm just now we seen. We have to left rotate the B to make it left heavy first. So we are going to convert this into the second condition. Then we right rotate everything. Okay, so these are the 3 cases that you should pay attention during the exams. Any questions? Questions, doubts? Okay. No questions, then we are going to move on to today's tutorial. First question is very easy. How can we trace the deletion of key 17? Okay, I think y'all are quite quiet today, so can participate more, okay? Easy question. Who wants to answer this? What happens if I delete 70? I'm telling you, the further we go, the harder the questions. 68 goes up, okay, so if I remove this, 68 goes up. Okay, what happens if 68 goes up? It changes the subtree on the right. If this goes up, then what would be the left and right subtree of 68?
66 on the left and 72.
Okay, 66 on the left, 72 on the right. Any other answers? Other answers? Okay, who agrees with Lian's idea? Agree? 1, 2, 3, 4, 5. Why do I have a feeling the rest skipping lectures? 6, okay. Who disagrees with the idea? No one? What about the others? Okay, so I will just reiterate what Lian's idea is. I remove 70, 68 will go up. Okay, when 68 goes up, 68, the left subtree is 66, the right subtree is 72. Agree?
Actually, don't we replace it with the successor of the node, that is 72?
Okay, if you replace with the successor of the node 72,
Yes.
so what will happen?
So 72 is it comes to the position of 70. And
Okay.
the rest of it stays as is.
Then what happens if 72 becomes here?
Oh, then 68 and 66 stay where they are.
Okay, this will stay.
Yeah.
If we are going to create a height balance tree,
Okay.
then
Yeah, then right.
then we have to right rotate. Okay. So yeah, the idea here is actually, if we are going to delete a node, oops, what happened here? Okay, if we are going to delete a node, instead of switching with the predecessors, we are going to switch with the successors. Okay, although this does not seem very intuitive at first, but we're going to generalize our algorithm to just the successor. After we swap this, then we are going to check if it's height balanced or not. Okay, so seeing here, you will have an imbalance AVL tree here, where the left subtree has a height of 2, the right subtree has a height of 0. And in this case, we are going to do the right rotate. Okay? So instead of swapping with the predecessors, we are going to swap with the successors. Now is this balanced? No? Why not balanced? Okay, left subtree is clearly, right? It has 1, 2, 3, 4. A subtree of height 4. Here it's just a subtree of height 2. So it's not balanced. What do we do now? We do right rotate. Okay? So this is very left heavy. So we're going to rotate this such that this node becomes your new root. Okay? When I do right rotation, I will take 52 as my new root. So that will go up, okay, assuming it goes up. And then I will have to connect, oh sorry, oops, I think I did something wrong. Oh yeah, I left rotate this first, and then this will go up. Yeah, something like this. Okay, so when I left rotate the left one, then your 58 will become your new node because that is right heavy, and then we are going to switch it with the root. So it becomes your 52 will become the root. And now this will give us a height balance tree. Okay? Any questions? Any questions? Sorry. Yeah.
So if we are performing an operation on a tree that is not height balanced, does it always have to be height balanced in the end?
If the tree is an AVL tree, then yes, it should be height
No,
balanced.
because this is not height balanced triangle.
Yeah. I'm not sure if the question asked for it. I haven't really seen the questions.
Okay.
But yeah, if the question itself doesn't specify that it is AVL tree, then you can just swap. But normally the questions in exams, right, it will expect you to do something more than that, okay? So that's why we have to create the height balance property. If it doesn't specify AVL, you can skip the height balance part. If it specifies, you should do height balance. Okay? Questions? No? Okay. No questions, then we are going to discuss about what we call a maximally imbalanced AVL tree. Okay? Maximally imbalanced AVL tree is a tree with the minimum possible number of nodes given its height h. So if I give you a height h, for example, I give you a height 3, what is the minimum number of nodes you can place such that it will become an AVL tree? I want it to be a minimum number of nodes. Okay, can try it. Stop here.
2 raised to h by 2.
2 raised to h by 2. Why is it 2 raised to h by 2?
I think there's a proof. I forgot the proof.
That's a proof.
Yeah.
Okay, any other answers?
7.
7. Okay, if the h is 3, why is it 7?
Because height 0 is unless you have 1 node.
Mm-hmm.
Then for height 1 you have 2 nodes. Because it's so your for every node, right, your left can have height h minus 1 and your right can have height h minus 2.
Okay.
To have the first case. So you just recurse outward. So for height 1 you have height 0 plus height minus 1, which is nothing, plus 1. So that is with 2. And then for height 2 you have height 1 plus height 0 plus 1, which is 4. And 4 plus 2 plus 1 is 7 for the last part, for 3 here.
Okay. Okay, that's also a solution here. So Andrew's idea is you can try to think of this as an imbalanced tree, then the left subtree and right subtree, there will be either one of these is h minus 1 or h minus 2, then you recurse. Okay, who agrees? Other ideas? Ideas. Kedwin, any ideas? Or what are you thinking of in currently? How to solve this? Yeah. I want the minimum number of nodes given a height balance tree H. 2h minus 1? Minimum number of nodes. If the maximum number of nodes we seen just now is 2h minus 1, right? Oh, 2 times h minus 1. Why is it 2 times h minus 1? Okay. Other ideas? Alex?
2h plus 1.
2h plus 1?
Because the left and right tree is just 2 nodes.
2 nodes. If it happens that the height is 4, if the height is 4, you can't say 4 nodes plus 1, right? Cannot. Okay. So okay, for this case, let's try to see some examples. Okay, I'll use a bit of Andrew's idea here. If it has only one level, height 1, how many nodes? 1 node. Okay. If 0, then no nodes. Okay. I'll assume this one. If it has 2 levels, then they'll give you 2 nodes. 3 levels. This is the most minimum way. You can't do anything less than this. If I just do 1, 2, 3, then this will no longer be height balance if I don't have this part. Okay. So this is 3 levels, and this one is for 4 levels. So I want you guys to try to remember the patterns here. This one is for 2 levels, 3 levels, and 4 levels is something like this. So how do we find the minimum number of nodes? Okay. So one key idea here is that for a tree to be maximally imbalanced, each of the nodes should be a root of maximally imbalanced trees. Why does it so? Proof by contradiction. If one of them is not maximally imbalanced, that means it is like some sort of, it's equally height, then I can always subtract 1, okay, to become maximally imbalanced, something like that. Okay, so for it to be maximally imbalanced, it should be the bare minimum for it to be a height balance tree for each of the nodes. Okay, so this bare minimum here, given a tree of 4 levels, I can see that the levels in my left subtree is just 3, and the right one is 2. If it happens that my right one has a height of 3, then this one, I can just remove one of them, right? So for it to be maximally imbalanced, this is the pattern. Should be 3, should be 2, for 4 levels. Okay, so this is just one example of trees here. Now if I try to expand this further, you will see that this left one, what is this? Just this part. Have you seen this before? Just the left part. The left part here is exactly the same as a tree with just 3 levels. Okay, the one you've seen just now. And the right one is exactly a maximally imbalanced tree with 2 levels. So this goes back to Andrew's idea. For a height h, the number of nodes there is simply the number of nodes in your left one, h minus 1, and in your right one, h minus 2. Okay, so you can see the pattern here. If I want to write this as the minimum number of nodes I need, there will be 1 node for the root, plus the number of nodes in the left, h minus 1, plus the number of nodes in the right, h minus 2. Okay, so I can write this as a recurrence relation, and this is what I will get. Okay, number of nodes, 1 plus number of nodes in my left subtree plus number of nodes in the right subtree, with the following base cases. Okay, so this would be the recurrence relation. Any questions? Questions? Nope. Okay, no questions, we can move on. So far I assume understand, huh? Okay, if we store height as an integer, each tree node will now require 32 extra bits because one integer is 2 raised to 32 bits. Okay? Can you think of a way to reduce the extra space for each node to be 2 bits instead? Now this is a fun problem. If we store height as an integer, it will be 32 extra bits. How can we just use 2 bits? Any ideas?
This is the height balance tree.
Yeah, for the height balancing. Because the height is needed for the rebalancing, right? So in this case, how do I reduce the extra space to 2 bits such that I can detect whether it's height balance or not height balance?
You just store the number of children each node has.
Number of children each node has. So that'll be 2 and 1. Okay.
Or 0.
Or 0.
That's 2 bits, right?
That's 2 bits. And then how do I detect if it's not height balanced? Because if I recurse upwards, for example, given my tree is something like this, I know that this is not height balance, right? Okay, so I check here, it has 0 children, 0 children. So what do I put as the value here?
0.
0. Okay, then this one also 0. Then here it has 1 child. 1. Here 2. How do I check if it's not high balance? Oh, this one I'll put 1 0 in favor of binary. Okay, how do I check if it's not high balance? Okay, I need to go to the child node. I see how many. What? Sorry.
You go to the child node and then you check how many child the child node has.
I'll check how many child the child node has.
Then you just keep going until it returns if it's high balance.
Okay, so what do I return? What do I store here? Because if you recall how the AVL tree checks if it's height balance or not, it will just run through from the path from that node going to the root, right? So if I recurse everything, then it will be very expensive. Okay.
Store whether the node is balanced left heavy or right heavy.
Sorry.
Store whether the node is balanced right heavy or left heavy.
Okay. So whether the node is balanced left heavy or right heavy, how does that work?
So you just assign three values. Right?
3 values. Okay. So if it's, for example, if it's left heavy, then it will be like 0 1. Right. Sorry. Let's just put. If it's left heavy, then 1 0 because the 1 is on the left. Right heavy, then 0 1. If it's neither, 0 0. Okay. How does it check here if it's balanced or not?
If let's say you insert a node, then you can update its like parent, right?
Okay.
And then like you can update all the way up, but then you like
Okay. For example, in this case, I'll just put here. Initially, all of them would be, in this case, it will be left heavy, right? So there will be 1 0. This case, it will not be either. This one is right heavy, so 0 0. If I insert a node here,
yeah, then the parent gets updated to
Okay.
heavy.
this one gets updated to 0 1.
Yeah, and it falls within bounds, so it's like okay.
Okay.
Then the parent above that gets updated to balance. And you like
It gets updated to balance. But this one is not balanced. How do I check if it's not balanced?
this one is balanced.
This one is balanced. Oh, it's balanced. Oh, sorry. okay. So let's put another one here. Suppose something like this. If I add it here, this will not be balanced indeed.
Yeah, then the parent gets updated to right heavy.
Okay, this one becomes 0 1.
Then the one above that gets it tries to like make it more right heavy, but then
Yeah.
that's too much.
Yeah. So this one cannot here. Okay, because this one is right heavy, but then you want to add something to make it right heavy also. So this one cannot. Okay, in this case it will detect that it is false. Yeah, that is a very interesting solution. Thank you, Kathleen. So that is actually the solution here. So instead of storing the height, we can store and maintain the balance factor itself. For example, I can put like 1 0 for left heavy, 0 1 for right heavy, then 0 0 if neither. Okay. So what happens here is I can now store as negative 1 0 or 1. Basically, this is left heavy, this one is right heavy. Okay, and that will be it. Okay. How this algorithm works is as proven by just now. Okay. Any questions? Should be clear, I think. Okay. One last question for trees. Given a pre-ordered traversal result of a binary search tree, how can we construct the original tree? Now this is a fun part which is covered in 131S. Any ideas? So let me just show a pre-ordered traversal here. How do I change this into a binary search tree? Ideas? This one is okay. Jiakai?
Take the middle element as the root of everything.
Okay.
Then you recurse on the left side and the right side.
And because on the left side and the right side,
Like you like for the left, the four left elements, you take the middle, you take it as the left sub tree of 32.
okay. So in that case, right? In that case, now my tree would be this one is 32.
32,
Then for example 20,
20.
then this one is 41, something like this. If I do a pre-ordered traversal, now my array will be 32 first, right? Because 32 will go first before the remaining, so it's not the same array. Okay, pre-order. I think you are referring to something similar to the scapegoat trees one. So how do I do this if I want this to be pre-ordered traversal? Wangche?
Wait, so as in this array is the pre-order traversal?
Yes.
We're constructing the tree, right?
Yes, I want to construct the tree from this pre-ordered traversal.
And 41 should be the root, right? Because your pre-order.
Okay, so everyone agrees 41 should be the root. Then what next?
Then you binary search for the largest, the smallest element that is larger than 41.
Okay, smallest element that is larger than 41.
Yeah, then you should get 50, the 65.
Yeah, 65.
65.
Then?
First element. Oh yeah, okay. Then first element that's larger than 41, which is 65, is the root of the right subtree.
Okay.
And then everything before that up until 41 is on the left.
Okay.
Yeah.
So this one is the left subtree. Then everything after that will be the right subtree.
Then you recursively call the traversal on both arrays.
Okay, yep, that's exactly the solution. Okay. So I will not explain this further, it's explained by Wang Che, okay? I think you guys can follow also. So once you notice which part is the left subtree, which part is the right subtree, just recurse. Okay? So something similar to this. Actually for this case, binary search is hard to implement because the arrays are not sorted. Okay? As you've seen here, it's hard to detect which direction to go. Okay? So in this case, we are going to do more of a linear search to find the first element that is going to be part of our right subtree. Okay? In this case, once we know which parts are less than 41, which parts are greater than 41, so this is some sort of like partitioning, then we are going to recurse, doing the same thing until we get this binary search tree. Okay? So I think one common question here is how can we construct a tree directly from a pre-ordered traversal? If you see in 1231, you need a pre-order and either a post-order or in-order, right? Okay, why can we construct directly? Anyone knows?
Because it's binary search tree.
Because?
It is binary search tree.
Okay, because it's binary search tree.
Yeah, and the left hand is always less than the right one.
Yeah, because actually the simple answer is we are handling numbers. In 1231S, you don't know how to compare one element to another one. That's why we need another traversal. In this case, as what Ferdy mentioned, it's a binary search tree. We know which element should be less than, it will be on the left. Greater than, it will be on the right. Once we partition, we know. Okay? So any questions?
Wait, binary search works, right? Because you can, even though it's not sorted, right? You know that everything on the left is less than and on the right is greater than. So
Oh yeah, yeah, actually yeah, it works. Yep, thank you. Yep, it works. So you can know if it's on the left region or the right region, yeah. Thank you, Andrew. Yeah, binary search works, sorry. Yeah, any questions on this? So this is a 4-step algorithm to determine the binary search tree given a pre-ordered traversal. Okay. If no question, then we'll move on to the second one. Second one is quite fun. We're going to do BFS and DFS iteratively. Has this been covered, BFS, DFS? Covered, right? Breadth first search and depth first search. Covered already? Okay. So breadth first search, depth first search. As you know, depth first search is most commonly used in a recursive method. Okay, once you have a child, just greedily recurse down. Okay, first child you see go down, first child you see go down. But now how can we implement this without recursion? How can we implement this without recursion? Actually, this is very simple. Okay,
no one is right, but instead of recursing, we use a while loop.
instead of recursing, we use a while loop. What do I put inside the while loop?
Like the current node. Then when you want to go down, then you call like the subtrees node. Like
Okay.
the sub node. Then you replace it. Then your connection will be like until, let's say like the current node is equals to 1, which is empty. So you reach the end of the list.
Okay. But how do I know what is the empty part? Where do I store the nodes that I want to visit? Like for example, given this thing. Whoops. whoops. Spoiled already. Okay, given something like this. If I want to, because right, so I start with 65. Then inside my while loop, what do I do? 65 can go to 52 and 72, right? So what happens? For example, for BFS, what do I put inside the while loop?
Like,
Because if I go to the while loop, right, for example 52 and 72, then I go to 52, then it will have 39, 58. Now where do I store this 39, 58 and 72? Like where do I remember what to go next?
and store it in the stack.
Store it in a stack. Okay, if I store it in the stack, I put 52, I put 72. Then for example, if I pull out 72, then I go down 68. Then I go down 66. Is this BFS or DFS? DFS, okay? Because if I put in the stack, anything that is last visited, if I last place it in the stack, that will go up first. So any child that is in the last place of the stack, I will visit that first. So that is DFS. So how do we implement DFS? Yeah, use a queue, okay? Okay, so yeah, thank you very much, Yifei Lian. And yeah, that is actually the solution here. So one quick method is, if you don't want to use recursion, then that will be using a while loop. Okay, that is a very common way here. So quick recall on stack and queue for those who forget, I hope not. You put A, B and C, but if you want to take one element out, which one goes out in the queue? A, okay, first in, first out. How about stack? C, okay. So first in, first out compared to last in, first out. Okay. Then we are going to see how BFS and DFS works. For BFS, right, we're going to traverse each level first before proceeding to next level, right? That is breadth first search. So every time I traverse each level, the children, I will add them to my queue. Okay, I will store the next nodes that I'm going to visit in a queue. How does it work? For example, I start from A. By default, I will add the first element, the root, into the queue to trigger everything. Okay. Now I take one element. While there are nodes in the queue, I will traverse to that node. So this is where the while loop goes. Okay. Whenever the queue is not empty, I traverse. I take one, I traverse here. I'll see that the children are B and C, I add to the queue. I go to B. Okay. I now traverse through the node from the queue. I take one. So I go to B. Then I'll see the children, they are D and E, so I'll add D and E. Okay? Then now I go to C. Why not D? Because C is in front in the queue. I haven't visited C, so I cannot go down deeper to D and E. Okay, this is breadth first search. So I go to C, then I will explore F and G. Okay? So this will be D, E, F, G. Which node should I visit next? D, okay? Because D is in front of the queue. So I'll take D, explore H and I. So now E, F, G, H, and I. This is breadth-first search. Okay? So, any questions on DFS? Questions? Nope? Okay. Now let's go with DFS. For DFS, we are going to go down deep before we explore the other children in the same level. Okay? So we are going to traverse each child first before we are going to backtrack. Okay? So as mentioned just now, we are going to store this in a stack instead of a queue. Okay? First of all, I trigger the whole process by adding the root inside my stack. Then I take one out of the stack. Then I explore the children, I add it here. Okay? For simplicity reasons, I put B after C so that I can explore B first. Okay? So I put B here, I pop B, then I will go to D and E. Which one do I visit now? D, E or C? D. Because D is on top of my stack. Okay, so I take D, I explore H and I. I take H, I take I, then I take E. Now I go to C, then I explore the children of C, F and G. Okay, so this is the first search. Any questions? Okay. No questions then, how do I implement the algorithm here? Are they similar, BFS and DFS? In fact, they are very similar. If I put the algorithm, the only difference here is the queue and stack. And that is the difference between breadth-first search and depth-first search. Okay? First of all, you put the root inside the queue or stack. And while that data structure is not empty, we pop one and we traverse each children. We add the children into the queue or stack. And that is DFS. Okay? So far, any questions? I think this should be quite easy. Okay? You see how similar the algorithm is, right? Okay? From now on, just remember one, then change the queue to stack. And that's it. Okay? Even no questions, then I'll bring you to a mouth-watering ride today. We're going to discuss about chicken rice. Okay? So imagine that you are the judge of a chicken rice competition. In front of you, you have n plates of chicken rice. Okay? Then you want to identify which plate is the best chicken rice. Okay? So for example, here I have a short illustration. So given here my chicken rice, okay, I want to judge using the following algorithm that is provided. First of all, I take the first plate, I put it on a table. Okay, so this is like the special plate, okay? Then I go through each remaining table, I compare with the one on the table. For example, if I eat this one, I notice that this is more delicious, so what do? If it's more delicious, yeah, I kick this from the table. I change with the new plate. Then I continue to the remaining. So the one that is left at the end of the whole process, that will be the winner. Okay? So, comes to the questions. Assuming that each plate begins, assuming that each plate contains n bites of chicken rice, okay, like n spoons of chicken rice. In the worst case, how much chicken rice is left on the winning plate?
What does the worst case mean here actually? What do they mean?
Worst case means here is, if you have to compare with everything, how much is left on the winning plate? Because you want to, as much as possible, you want to have the winning plate preserved for others, right? If it is very delicious, you know, it's like, I'm not sure if you all watch, like, there's a series called Upin Ipin, the Malaysian one. So like, there was one moment that there's like this durian contest, right? And then the judge was like eating the whole durian on his own. Basically, if it's so delicious, you want to share to others, right? So in the worst case, how much chicken rice is left on the winning plate? One bite? Anyone doesn't agree with one bite? Okay, so yeah, there will be one bite. So in the worst case, if this happens to be the winning plate, right, you have to compare this with everything to know that this is actually the winning plate. So that means you will have to compare n minus 1 times. You eat n minus 1 times, so remaining is 1. Okay? Because it's so delicious, you don't even mind to eat more, but others will not get the plate. So now comes the second problem. What if you want to share to others this winning plate? How do you know which one is the winning plate and try to maximize what is left in that winning plate? Now this is the fun part. So given that I've already shown you a naive solution, you test the winning plate with others. In the worst case, there's only one bite for 100 people there. Okay. So now, how do I maximize the number of chicken rice left in this winning plate? Suddenly becomes quiet eh. How do I maximize this? Okay, 并肩.
Split all the plates into groups of two. Each group compare each one to see which one is better. Then like put all the like winning plates, and then like put all the losing plates aside. Then recurse on the winning plates until you reach one plate left, which is a log n solution.
So we compare two plates. Then winning one I keep, losing one I throw. Then I recurse on the winning one. Okay. Who agrees? Who does he agree? Okay. Okay, I'll keep that solution. Any other solutions?
What if you have like you go through each plate once, then every time you rank the plate by a number, like numerator by a number.
Okay.
We take the highest numbers and we tie break them.
Take the highest numbers, then you tie break. Okay. That will be a subjective algorithm. Okay. And then what if the judge is like, for example me, I am an indecisive person, I eat, oh this is delicious, I give a 10. Oh this is delicious, I give a 10. Then it happens on my whole iteration that then all will be a 10. How do I solve this?
Then that's a skill issue.
Lian XP minus 100 for today. Okay. Okay, I'll keep that also, thank you. Wang Zhe?
You eat sugar rice sequentially, right? So you don't have to compete compare, just eat sequentially. Then you rate it by how good it is to the previous plate you just ate. So let's say you have 3 plates. You compare first plate and second plate. If second plate is less good, you just say it's less good than the first plate. They compare the third plate with the second plate because you just ate it.
Okay.
So afterwards, you take all the plates that you have ranked to be better and tiebreak it that way.
Okay.
So you see
So given for example I have 5 plates here. Okay, 5 plates. There's 1 plate, 2, 3, 4, 5. First one I eat. Then second one I'd say this is less than the first one.
yeah.
Then third one I would say this is greater than the first one. The previous one.
Yeah.
So given this case, for example this one something like this. How do you know the winner?
You take all the greater ones and do the same thing again
Greater one the same things, okay?
until you get a case where everything is like exactly one single order. So like let's say you do it until you have everything is less than the next
Okay.
plate. Then you just take the first plate. I think it's the first plate. Yeah. And then if it's all greater than, then you take the last plate. Because that's guaranteed the winner.
Okay, yeah, this one actually also works. But what if there will be an equal one? Again, if the judge is indecisive, of course that is a skill issue, but then what if there will be an equal? But okay, this algorithm works also. I will keep this. Other solutions? This one works also. Okay, if not, let's just discuss. Okay, let's start from this solution first, okay? Because I'm not going to the skill issue part later. Okay, let's go into this one. What is the worst case for this? The worst case is what if there will be like this one is less, then this one is greater. Okay, if I follow Wang Zhe's solution, I will need to put all the greaters together. So that will be, in every time I iterate, I just lose 1 plate. Then every time I iterate, I lose 1 plate. So it happens to be, at the end, if it happens that every time I iterate, only 1 plate is less than, then that will be n minus 1 also. So it doesn't really solve the problem of reducing the n minus 1 bytes. Right? So it happens that if I take one, by the end, there will be n minus 1 bytes. So n minus 1, there will be 1 byte in the end. That is the worst case for this. Okay? And the skill issue part, that one is a bit subjective, okay? So in this case, I'll try to do what Ping Jian's solution is. Ping Jian, right? This one? Yeah. So if I group them by pairs of 2, then I compare the winning one I keep, the losing one I throw, then the winning one I recurse. That is exactly what happens. That is exactly what happens in competitions. Okay, you have football competitions, you divide them into groups of 2, rounds of 16, rounds of 8, then quarterfinals, semifinals, then finals. Why do we do so? so that we want to reduce the amounts of players playing multiple times again, because that would be very tiring. You don't want the winning team to compete with each and every team, right? So in this case, for example, I have n bytes here. I compare first two, second, then the next two, next two, next two, next two, so on and so forth. Then I take whichever is winning. For example, in this case, one is winning, so there will be n minus 1 byte, the remaining ones. Okay. Then I compare the winning ones, there will be another byte. And finally, I'm left with just 2, so that will give me the final decision. So in this case, I just need 3 bytes to go up, compared to the first algorithm where I need 7 bytes. Okay, this is how I can maximize the number of bytes in the winning play. So it will be correct, as what Ping Chen mentioned, the runtime is not log n, but then the bytes will be just log n. Okay? Yeah, the bytes are just log n. Yeah, the bytes is just log n. Yep, correct. So we are left with this case. Number of bytes will be just log n, but number of bytes you need to eat as a person, you need to eat, right? Is that every time you recurse, you will have n bytes, n over 2 bytes, n over 4 bytes, n over 8 bytes. If you sum everything here, it will be at most 2 times n. Okay? Can refer to first tutorial on how it is 2 times n. Second tutorial. Okay? Any questions? So I think this one is quite intuitive because it follows like the normal FIFA World Cup kind stuff. Okay? So finally here, can we design an algorithm to maximize the amount of remaining chicken rice on the median plate? Median plate. So I don't know what happens to the competition now, but then we want the median plate now instead of the best plate. How do I do this here?
Just skip it out. Don't need that.
You skip it?
Keep it out. Just remove it from the array. Then the rest of the things you do whatever.
Okay, you can just remove from the array. That's a good one. But how do I know which one to remove?
And you just find the mid because the median is like the mid element. So you just find what the mid element is, then you remove it, and then you just refill the array.
Oh, what if it's not sorted?
What if it's not so?
It's not sorted, right? If it's sorted, then what's the use of a judge? Yeah. Randomly choose one median. Okay. Yeah, how do I know which plate is the median? Round robin. That one is if the judge is very hungry. Yeah, Kevin. Okay, how does quick start works here? Okay, so randomly choose a plate, then you compare. What happens after comparing? Hmm. Yep, that also works. So you use quick select to find which one is the median plate. Okay. So once you partition, you recurse and recurse. Okay. So
In the worst case, the dish is all gone. Right?
yeah, the worst case will be if like happens to be you take the pivot in the wrong direction. Yeah, but
No, if you take the no wait.
yeah. The worst case you will have also n minus 1 bytes, but that is the worst case. Instead of you take one, then yeah.
What if you do like the tournament style, but once you reach like half the players available, we know that the median will definitely be in that group. Then we do like the line solution.
Actually, I don't think that's true. It's like, it's not transitive.
Yeah, if the best is paired with the median in the first round, then the median is eliminated from the first round itself. Right?
This one is actually a solution here. So the median might not be there, and the median might not be the one selected there also. So that will also contribute to a problem. Because you can try to find cases where the median can be knocked out in the first round. If it happens that there is another element greater than the median placed in the first round, then the median is knocked out already. Then the others will continue. Okay? You can try to construct a case there. Sorry. Okay, so let's proceed with Kathleen's solution first here. So for example here I have a quick select algorithm. Okay, I have these chicken rice that are numbered now 7216824 assuming that I know the ranks because or else I just switch, then no one will know what it is. Suppose I know the answers here, but as a judge I don't know so I will take one, I will compare with the remaining one. So I choose a pivot here, then I compare a partition. But every time I partition, right, this pivot will get n-1 bytes eaten. Why? Because I will need to compare this to all the remaining chicken rice. Is this okay if the pivot got eaten? Why is it okay? Yep. So it will depend on the expectation itself. The chance that the pivot is the median is 1 over n. The chance that it's not the median is n minus 1 over n. And if it's not the median, if it happens to be the worst one possible, don't care about it anymore, right? We only care about the median. Okay? So, okay. If we choose the pivot at random, the expected cost on the median plate is the cost of how many bytes you eat if you're taking the pivot plate, okay, times the probability that this plate is the pivot, plus the cost if the plate is not a pivot, times the probability that it's not a pivot, okay? So, the median plate can be a pivot, can also not be a pivot. If it's a pivot, then you will have 1 over n chance, right? Because it's 1 plate over n plates total. So you choose 1. If it happens to be the pivot, then you might have to spend n minus 1 bytes. Okay, if you take the median as a pivot, then you will have to spend n minus 1 byte. The probability of the median being a pivot is 1 over n. What happens if it's not a pivot? Then the cost that it's not a pivot is basically just 1 minus this 1 over n. Sorry, this one is the probability of it's not pivot times the amount you eat in every iteration. There's only 1. Okay, that's only 1. If it's not a pivot, you're just going to take ones, compare with the pivot. Take ones, compare with the pivot. Take ones, compare to the pivot. Okay, and the probability is not a pivot. It's just n minus 1 over n. Okay, so it's a greater probability here compared to it being a pivot itself. So now what happens here is, magically, the expected value here is just if I expand everything, this will be 1 plus 1 minus 1 over n, that's 2 minus 1 over n, that's less than equal to 2 bytes. So the expected one is 2 bytes. Although arguably, you can have the worst case of n minus 1. Okay, if you are talking about worst case, that will be n minus 1. But expectedly, we can have just a maximum of 2 bytes. Okay, this is expected, yeah.
This is one partition, right?
One partition only, yes.
So this is multiplied by log n.
No,
Because
you don't multiply, yeah.
Yeah, so we do the whole thing log n times.
Yeah, you multiply by log n, yes. Okay. Because if it happens that it's not the pivot, then you repeat. Okay. But if it's the pivot, then it stops.
Yeah.
Okay. But in that case, there will be n minus 1. Yeah. Okay. So, at every level of recursion, there will be 2 bytes. Then how many levels? That is the log n levels. Okay. So that will give us the O log n bytes. And the total that you consume as a judge, that will be On. Okay, because of this log n recursion. So, okay, any questions?
I think like in the end you will always find the median between the before, right?
The n, yeah, if you recurse the quicksort, you will always find the median.
I mean as a pivot or
Yeah, it will be actually as a
so
pivot.
if it, in the end it become the pivot, like it will always, it can be always end with one place only, I guess, or in the worst case.
Okay, so there's actually a dispute here because I'd say that if you consider the current algorithm you studied, it will need to be a pivot, right?
Yeah.
But basically, if you know that your current element is, for example, the 5th out of like say 10 elements, right? If your current element say the 6th or the 4th one, then you can just move one, right? Sorry, you can't move here. Sorry, yeah, it should be the pivot, yeah. Sorry, it should be the pivot, yeah. Sorry. So yeah, in the case that it will be a pivot, but then if you already take it as a pivot, right? In every partition, you expect that it will be at least like half or something like that, right? So in that case, the number of bytes you will eat will be lesser.
Yeah,
Yeah, so at every partition it will be less until you actually reach that the median will be the pivot, then it will be less than n minus 1. So it happens that this expected value, since it's expected, right? So we already consider the probability inside, the 1 over n and the 1 minus 1 over n. So it happens that this is the average of it will become the pivot, or if it's not the pivot, then we recurse that. So we already counted it also. Sorry for the confusion just now. Yeah. So the possibility that it's not a pivot and the possibility if it's a pivot is already counted inside the expected cost. Okay. I think it might be a bit confusing, but yeah. In the worst case, then yeah, it will be the pivot. Yeah. In the worst case, you have to traverse. But in the expected case, then we will count it as the 1 over n and the 1 minus 1 over n. Okay. Yeah, expected ones.
Yeah.
So we consider probability already.
The worst case is not the median becoming the pivot, but like if you choose the wrong pivot, like if the pivot is like
Yep. Yep, the worst case if you choose the wrong pivot. So how do we tackle the worst case? Randomize. we choose a random pivot, then we will expect that it's just O log n bytes by randomization. Okay. Questions? Okay. If no questions, then we can take a break for 5 minutes before we will move on to the remaining questions for 4 and 5. Any recommendation for 4-minute songs? Okay, I'll randomly choose from 4 people of this front row. Choose one person for a song recommendation. Let's chill a bit. If no recommendations, I'll play Baby Shark for 10 hours.
No.
Play the top G song.
What top G song? Top G. Oh no, my YouTube is no longer premium. Top Gun? Why is it Andrew Tate?
Hey, you know that?
Yeah, after recess week we will start with songs lah. Okay. To chill out. Okay. Have anyone tried the midterm past papers? Or is it uploaded? I think it's uploaded, right? Oh no.
It's not in files yet.
Oh, no files yet. Never mind. I think I can. Wait, I don't have the files. I used to have but then my laptop got reset like last sem because it broke the hard disk. Let me try check later if I kept it somewhere else.
What's the syllabus?
Hmm?
Makers?
Oh, I cannot. So let's start the remaining today. On question 4. Question 4, we are going to talk about economic research. So for example, if you are an economist doing a research on the wealth of different generations. So here you have a data set. The first one is your unique identifier, second one is your age, and third one is the wealth. Okay, some sort of like net worth or something. Now given this case, we want to try to divide this data set into age ranges of equal wealth. So each range we want to ensure that the amount of wealth there is equal. Okay, so something like this. If I convert this, ID1 and ID3, the sum is 151,000. ID2 and ID5, the sum is 193,000. Then ID4 is 109. Okay, although they don't sit equal, but this is like some sort of the as much as possible equal that we can get. Okay, so how do we do this?
Can we use a greedy algorithm?
Okay, greedy algorithm. How do we do the greedy one?
Okay, so wait, sorry, how many ranges do we have to divide it into? Is that k?
K, yes.
Okay, so we divide it into k sort of roughly equal age groups,
Mm-hmm.
and then we expand the age groups as required to, sort of equalize it then. And
We expand the
makes
age groups as required.
sense.
How do we know the age groups in the first place? Because if, for example, I divide them, right? For example, I know that the ages are, let's take a very rough one, 0 to 99, for example.
Mhm.
Okay, then that means 100 different ones. I can divide them by, for example, k is 4, so 0 to 25, 25 to 50, and then I will know that this one, 25 to 50, of course, they will be much larger than 0 to 25, right? So how do I determine how to group them together?
So you can increase, say 25 to, a little more till it's, let's say, equal to 50.
Because if
equal
I-
to the,
If I increase 25 a little more,
Mhm.
then what if I have 26, right? If, for example, my first data set is 26, 26. Of course, if my data set is not adjusted, right, it will fall under the 35 to 31. Then if I adjust this, that will be 0 to 35, I will add to like 0 to 37. Then I will have to move this 26, go back to 0 to 27 again. So that will come another complicated part of the algorithm there. So in the sense that the greedy might work, but then there is some steps that we have to do later. So this one is quite challenging, I say. Yes.
I can sort it maybe.
Hmm?
Sort
Sort? How do you sort?
sort the age.
Do you sort the age?
And then like if there are n people and you want to make k groups, like every group you have n per k, n divided by k people, like just take n divided by k people and then n divided by k, n divided by k.
Actually, the n divided by k1, it's not really the people that we want to divide them equally. It's more into the wealth that we want to divide equally.
Okay.
So that's where the problem actually comes. If we want to divide the people equally, then there will be the greedy algorithm also works, because that will ensure that it will be equal. There's something called the 2 optimization, which I think a lot of people did in PS2. Okay, the greedy one for PS2, that actually works if we want to divide them by the same amount of people. But now we want to divide them by the same amount of wealth. So that's where the problem is.
We can do something similar, right? So we find the sum for the wealth, then we divide k,
Okay.
and then after that we just so we start from, so we sorted by age already at the start, so we just start from age 0, then we just keep adding to the first group until we reach the total wealth over k.
Yeah, that actually also works. Yeah. Yep, that actually also works. Yeah, that actually also works. So for example, if you have like k groups, then if you sort this by the age, then you greedily insert into the first group. Those kind, yeah, that also works. That works. Any other ideas? Okay, also works, thanks. Well, power of teamwork. 3 ideas merged into one. Yep. Ideas. Who agrees with the idea? Agree. Okay, those who don't agree, shall you? Okay, disagree. Shall
No,
you?
I
Oh,
agree.
okay.
with that,
agree. Shall you, Lian? Ideas? No. Okay. So I'll provide a new perspective here on how to solve this. So first one is similar to the greedy one. We want to try to sum up all the age groups, all the wealth here. We want to sum up all the wealth and divide it by the k, so that we know roughly this is the threshold that we want. Okay, so by dividing the sum by k, that will give you an estimate of about 151,000 in each group. Okay, so what next? Now what next is, I want to try to find the smallest ages, the age that is smallest, so that the sum of all wealth here is at most the 151,000. Okay, so I want to find up to which age is the sum at most the 151,000. Okay, if I try to do this algorithm, if you see the way I plot this out, anyone can figure out which algorithm I'm going to use? Can figure out? If I want to find the smallest age group that has the wealth at most 151,000, I'll take one as a pivot, then I partition the ages based on that pivot. Right. So in this case, for example, if I take as pivot I think is it this one that I take? Yeah. If I take this as a pivot, the median, I will take this as a pivot. Then I partition based on that median age. Okay. Once I get the median age, 32, I partition them. Now there will be left and right. Okay. So I just need to check the total in both left and right partition. How do I check the total? In the left one, it's easy. Okay, if I go to the left, if the sum of this is less than 151,000, that means I go to the right. Okay, so I just need to total this. I see that. Okay, if your target happens to be on your left, your 151,000 happens to be on your left, then you can just recurse. Okay, you see that the total here is 151,000, so actually this one is just one group directly. Okay, but if it happens to be less than 151,000, that means you can go to the right first before going to the left. If it happens to be greater than 151,000, like 152, that means you can recurse on this. Okay? Now what if it's on the right? To check it's on the right, I will have to find the target on the left first, the sum here. Then I subtract my target. For example, if I want it to be, for example, 200,000, I have to subtract by the sum here. Then I find if the target is within this range here on the right. Or else, right, if I want to find 200,000 here, then might not be what I want here. So I have to subtract by everything on the left. Then I find if that subtracted value happens to be on my right. Okay? If it happens to be between here, like, then we recurse there. Okay, so it happens to be between your recursion. Or one better case is actually we don't have to check the right one, just check the left one. Okay? If you want to recurse to the left, go to the left. If you don't want, then you recurse to the right. That also works actually. Okay? So we can also use quick select for this, and it can be done in O(n) time. Okay? Because that's the case for quick select. So given that we now find one target, if we already know that this age group will be for one target, we can recurse on the remaining ones. Okay? One target, keep out, then recurse for k minus 1 targets. That will give us a runtime of O and k. Because we are an O(n) algorithm, k times for the k targets that we want. Okay? Because we have one age group, we kick out, then the remaining we are going to recurse. Okay? So far everyone following with this? Yingjian?
So what are these targets exactly?
Targets are actually in that case, right, I want like 151,000. I want a cutoff on 151,000. So I want to know, right, which ages will reach my cutoff of 151,000. Okay, so I want to know, given that my ages here are already partitioned, right, I want to check 151,000 is up to which age. Then I cut off there. So that will be one group. Then the remaining, I will see 151,000 is up to which age. Then I cut off. I go to the remaining. So that is what I'm going to do. Okay, I try to cut off 151,000. Okay, does that answer? No. Yeah, okay. Okay, any other questions? Doubts?
So if just now what if so you have so you pick a pivot, then you're comparing, you're checking whether the left side is the target, is it?
Yep, those kind of stuff.
Then the right side can also meet the target, right? In that case.
Yeah, but we are trying to finish the left first.
Oh, okay.
Okay,
Yeah.
so we are trying to finish the left first, then we can recurse. Well, actually, your algorithm there, it works for the later versions. Okay, it works for the later versions. Because this is actually a naive solution. Yes.
Sorry, so to clarify, right, so for all of the groups that you choose from this algorithm, all of them will be above the target, right? Except for the last one?
All the groups that I choose here should be the less than the target that I choose here.
Less than?
I think at most the target. At most. So given that 151,000 I cut off there. 151 I cut off. Or actually if you want it to be greater, then you can find the least element that is also greater than that. That also works actually. Yep. At most some move, okay. Yeah. Yep. Okay. So far, any other questions?
I'm a bit confused on the pivot part actually. Why are you using as the pivot?
The pivot here we take as the median element actually. Yep.
Median element of the age?
Median of the age, yes. Based on the age. Okay. Later we'll see how to optimize this also. So that comes another problem here. How do we actually optimize this answer? How do you optimize quick select? Ideas? Some template ideas here. Optimize quick select. Okay. Multiple pivots, okay. That is for optimizing quick sort. If we only want to stick with one pivot, then of course one way is to randomize the pivots. Okay, that's actually one. But then if we want to find the median, then of course we cannot randomize this. This one is a template one. But the other one is actually we can try to, this one I will scrap this because it's not relevant to our question. But then the other one is, what if we just calculate whichever the cutoff is up to the rest that we want, okay? Like 151,000, then we cut off to 303, then we cut off to 4,000, something like that. What if we can cut off that way? Then that will help our data here. Okay, so we can just make the breakpoints directly there. We find the breakpoints directly, then we run the quick select once here. Okay, so instead of doing quick select, let's try to imagine ourselves doing a quick sort first, because the quick select part is a bit confusing without this. So if we want to do quick sort, but then now let's partition them into k pieces based on the number of elements, based on the number of people there, instead of basing on others. Okay, suppose I want my k is equal to 4, then I partition them to something like this. Okay, suppose. Yep. Now if I think this one is a bad choice of partition. This one should be like the same ages lah. The increasing ages, those kind of stuff. But then suppose this way. Given that my breakpoints are calculated in first, in this case, right, my sum is 808,000, so my k is 202. I just need to find which age ranges will have my 202, 404, and 606. Okay, forget the diagram here. I think I made a mistake in the ages. Okay, I just need to find which age range will contain the 202, 404, and 606. So what do I do now? I'll try to total each of these. Okay, I'll try to total each of these, and then I will insert my breakpoint into whichever partition that contains the total that I want. Okay, given that now the ages are sorted out later, this one is wrong. Okay, so I will find whichever partition does the breakpoint 202, breakpoint 404, and breakpoint 606 fall into. Okay, in this case, right, 202 will fall under this breakpoint, 404 will also under this breakpoint, and then 606 will be under this. Okay, something like this. Now, to actually determine which range will be cut off, we're going to insert the algorithm directly. Okay, inside the subarray, we're going to recurse. Okay, I'll fix the parts later when I fix the slides. Okay, so quick recap. Partition, and then we are going to insert the breakpoint inside the partition that we think contains the total, and then inside this partition we are going to insert the furthermore until we reach the total that we actually want, the specific ones. Okay, everyone with me? Okay, everyone with me? So it's like 2 times of first for every partition, then now inside the partition we find whichever is our cutoff. Okay, so comes to how will our runtime be for this case? ON? 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 Okay, I'll keep the ON first. So first of all, to partition all the elements until we reach k partitions using quicksort, okay, that will take n log k time, correct? Okay, because I just need to do log k iterations to determine the partition given a correct pivot, randomized pivot. Okay. Second one is we want to sum up all the wealth. That will be the OM that you mentioned. Okay, because in each partition I want to know what is the sum there, so that I can divide the breakpoints into which partition I want. Okay, everyone with me? With me? Okay. Now, to search which piece that the targets belong to, that will take k log k time. Anyone knows why it is k log k?
You have to go through all the partitions.
Go through all the partitions,
Sort the partition.
sort the partitions, no. So if I know the sum here, I can keep a specific array called cumulative sum. So 149 plus 47 plus 260 plus 352. So that will be a cumulative sum here, cumulative sum here, cumulative here, cumulative here. I can check with the middle one. If it's greater than the cumulative middle, then I will go to the right, or else we'll go to the left. So why is it log k? Because we can do binary search. Okay? To search for which piece that contains the target, we can use binary search. There's log k times we have k different targets that we want to place inside, k different breakpoints. So that will give us the k log k. K breakpoints times log k for binary search. Okay? And finally, to actually find the exact target position, given that now our partition, if we assume that it is already balanced, okay, because of the randomized pivot, then we will have a n over k, n over k, n over k, n over k, right? Now inside this, to actually search which is the target position that we want here, we will need to just traverse the n over k, we place inside, and that will be repeated for k breakpoints. So that will give us O n over k times k. Okay? N over k times you have k breakpoints. So that will give you O n time. So total runtime? Which one is the most significant here? The n log k. Okay, so the total here is on n log k. Questions? Questions? Now, I will go back to the idea of wait, sorry, this part. I forgot to change this. Yeah. So I will go back to the idea of Andrew here. We are doing quicksort, right? But actually we can do better than quicksort. We don't have to do quicksort to divide them into partitions, then throw the breakpoints into the corresponding partition. Instead, what we can do is, directly after we know the pivot, right, the quick select, we can just directly throw the breakpoint, either it goes on the left of the pivot or on the right of the pivot, and then we will divide the cases. Okay, so that happens to what Andrew taught just now. You can sum up the left and also sum up the right cases. Okay, so in this case, instead of doing quicksort, we can do quick select, we divide, then we throw the breakpoints directly from the pivot. Then we recurse. Okay, so we don't have to quicksort them into partitions, then do the multi-step process. Once you can do quick select, you throw the breakpoints, then on each of the partition and the breakpoint, we can repeat the algorithm until we actually find the case where okay the breakpoint will be stopped here, and that is actually the solution for this. Okay, so far any questions? I think the last part might be a bit confusing. So quick sort is to divide them into k possibly equal groups so that I can sum them up. I throw the breakpoint inside, then I find whichever is my cutoff. Okay, but I can sum these three pieces together into just a quick select. Okay, I quick select based on the median. I throw the k, the target, to either the left or the right, then I recurse. That is also a solution here. Questions? Questions? Okay. If no questions, then we'll move on to the very last. I think this one is actually much more intuitive, I'd say. So you're given the root of a binary tree with n nodes. Each node is assigned a unique value from 1 to n. Okay. You are also given an array of queries of size m. You have to perform m independent queries on the tree, where in the ith query, this is what you're going to do. First of all, you remove that subtree, okay, that is rooted at the node with the value queries e from the tree. Okay, so basically this tree, you remove them, and then you return an array that contains an answer for each query. Once you remove this query, and once you remove this subtree, what is the height now? Okay, so you can think of like you want to do multiple queries. For each query, you remove the specified subnode, you remove, and then what is the height now? You remove, what's the height? You remove, what's the height? That's actually the question. So something like this. If I want to say I want to remove 9 here, okay, how do I remove 9? If I remove 9, then this will be deleted. What is the height now? Anyone can tell me what's the height if I remove 9? 3, okay? The height will be 1, 2, 3, so that will give me 3. Based on the definition that's provided in the question, okay? So if I remove 2, then the height will be 2, and yeah, that's actually the algorithm here. And that's actually the problem here that we want to find. Okay? So given if I have multiple queries, for example, I want 9, 2, then I expect you to return 3, 2. Where it means that when you remove 9, the height will be 3. When you remove 2, the height will be 2. Okay, so this is our expected algorithm. So anyone has ideas how to implement this? Okay.
What I did was initially I stored the tree into a hash map. So the key is actually the child, value of the child, and the value of the tree, the parent node. So it can be either the left or parent node. And then I create a function that calculates the height of the tree. Then for every query in queries, I will actually assess the hash map and set the left or the right of the parent node to null. And then I put the tree into the height function to calculate the height.
Okay, yeah, that actually works also.
Theory.
But what about the height function? What is the runtime of the height function?
I forgot what. It's OH. Yeah. I think
Actually, to determine the height, right, you might have to traverse the nodes.
Yeah.
Okay, so that will be ON.
Oh.
ON minus the query, but then still, if it's like large one but you remove one, worst case ON. Okay, so that will be an ON. Yep, that's actually a good solution. But use hash map. That's a more advanced topic we'll touch later. Thank you very much, you. Others? Yeah, that's actually a working solution.
My
Hash map.
TLEs. The TLEs.
Okay.
The time limit.
Oh, TLE.
Yeah.
Oh, you tried. Okay, TLE. Okay, solutions? Others? This one is fun actually. The TLE is actually because of the height function, I'd say.
Because every time I do because the degree are very large,
full of queries, so every time you
So quiet. Vincent? Yeah. No.
No, because
Oh.
one thing takes an unbelievable amount of space, but you could like you're given a tree, so before you actually answer the query, you recurse through the whole tree and you find like the highest height that is in the tree and the path that is needed to get to the highest height. So for this tree, it will be like 5824 and 5826.
Mm.
Then for each query, then you store all of them in like a list of like possible combinations to go to, and then for each query, you go down the combination in descending order until you find one that doesn't have that node that is in the query.
Okay. Yep, that actually also
I
works.
think
And then
really
yeah,
well.
the space yeah. But that's actually a very good implementation. Thank you very much, Pintian. In fact, I will improve on what you are saying just now lah. Okay, the algorithm is similar. Okay, so I guess I'll just discuss for the interest of time. So one naive solution, as usual, we have to discuss the very basic ones. If you want to remove D, okay, if you want to remove D, I remove this and then I find okay, so I want to remove D. Whenever I encounter the D here, the one that I want to remove, then I return -1 here. Okay, because technically I remove this. Okay, but if I don't encounter, I will actually calculate the height of the tree. So basically what I'm doing here is I want to calculate the height of the tree with one condition. If I meet the node that I want to remove, I return -1. Okay, similar to your count nodes, but then now we are doing count height, something like that. Okay, anyone knows how to implement this in code? Count nodes, everyone know how to implement, right? But what about count height? So count nodes, right? You're going to count the left subtree and the right subtree, but what about the height? Yeah, so we are going to find the maximum of the left subtree height, then the right one. So doing the recursion, if I meet D, the one that I want to remove, then I remove this. Okay? If I meet the base case, I will put a 0. Then I will go up. Okay? So the maximum is the maximum of -1 and 0. That will be just 0. I add with the new node, the node of B. So that will be 1. 0 plus 1. Okay? Then I will recurse, going to the right one, 0. Going to G, I is 0, then J is 0, then I recurse all the way. Maximum of 0 and 0, that will be 0, plus 1, that will be 1, plus 1, that will be 2. And finally, what is the height of A? 3, because maximum of 1 and 2 is 2, 2 plus 1 will give us 3. So this is a very naive solution, which is similar to the height function on how to determine the height. Okay? Questions on this? Now, the runtime here, every time you want to remove, you will need OM time. Thus you have to traverse each and every node, and if you have M queries, your runtime will be OMN, which is quite large. Okay? So this happens if you are doing this on like some coding platforms, then this will be the time limit exceeded because it's quite large. So how can we improve this algorithm? So let me just provide a brief intuition of what we are going to do here. Suppose I want to remove node D here. Let me introduce two new terminologies. Depth is actually the number of edges that we are going to get from the root to the node that we want to remove. Okay, so the depth of node D is from the root, how many edges do I need to get to D? So there will be 2. Okay. Now the height at node D is from node D to any node below, what is the maximum number of edges to get, the longest path going downwards. So in this case, anyone can tell me the depth of D? 2. The height? 2. Okay, so depth 2 and height 2. So suppose I want to remove D here. If we remove D, what is the maximum height of the tree? Okay, I know that there are other nodes of the same depth, so I just need to check the remaining nodes here, which one has the maximum height of the remaining nodes. Okay, understand? So if I want to remove D, I check every other node that has the depth D, the depth 2, the same depth as D. I see which one has the maximum height. Okay? In that case, I will just need to return depth plus the maximum height. Understand? In this case, right, height of E is 0, height of F is 0, height of G is 1. So what do I return? I return the depth 2 plus height of this 2 plus 1. That will be 3. Okay? But then comes the problem. How do I know which nodes are the same depth as D? Huh?
Yeah, pre-compute.
Pre-compute it. Okay, you can pre-compute. Pre-compute, that means you will take one time to traverse. Okay? So that is actually the part here. If we want to calculate the result only once, but then it works for all queries. This is what we call as pre-processing or pre-compute. Okay, so given that you have n queries on the same tree, right, you can calculate everything once, and then we perform the query later in a faster time. This is to reduce the time for each query. Okay, so pre-processing here, I will construct a tree that contains the result. If a node is removed, what is the height of the tree now? Okay, I will create another tree. Each node now will now store, instead of a list of combinations that just now Ping Chen mentioned, I will now store just the height. Like, I will now store the answer. Okay, instead of storing the combinations, I will now store the answer. If I remove this, I just need to return the answer. If I remove this, I return the answer. Okay? So to obtain the query, I just need to find what is the position of the node in the tree, then I return the value. Okay? So something like this. Given at depth 2, so once I pre-process this, I can know which ones are depth 1, depth 0, depth 1, or depth 2, and so on and so forth. But then, or else you can also do the normal traversal, either in order, pre-order, post-order, those kind of stuff. Okay? So you traverse, every time you traverse, the depth will increase, right? Now, for each one of these, we're going to find, if I remove that node, what is the height now? Okay? Actually, we will start from the bottom, but then for now, we can stick with the middle first because it's more intuitive to see. Okay? We have D, E, F, and G. Okay? These are nodes at depth 2. Okay? Everyone following? These are nodes at depth 2. So I can try to pull this out, and for each of the nodes, I will keep the height here. Okay? Instead of storing all of these heights, I can just store the two longest heights, the two greatest heights. In this case, I can disregard E, disregard F. I will just store D and G. Why do I store D and G? If D is removed, I'll just take the height of G as the result. If G is removed, I'll just take the height of D. If E and F are removed, then I will take D. Okay? So it happens that I just need to store the longest path and the second longest path. Because if I remove the longest path, I will refer to the second longest path. Okay? So in this case, can anyone tell me the height of D? If D is removed, what's the height? 1. If E is removed, 2. If F is removed, and G is removed, 2. So these are the heights that I will store as the answer. Now since we want to directly return the answer, what I can do now is this answer, I will just have to add with the depth. Okay, going down is 2 levels, so I'll just add everything by 2. That will give me 3, 4, 4, 4. Okay, so now you see the algorithm here. If I remove D, I just need to return 3. I remove F, I just need to return 4. Okay, so I'll do this for each and every node. For H here, I will do something similar for K and L. Then for B and C, and finally, what happens if I remove A? What happens if I remove A? Everything will be empty, right? What happens if I remove an empty one? An empty one, I will return a negative 1. Why do I return negative 1, not 0? Because by the definition here, for this question, if I just have one node, then there will be 0. But if I don't have any nodes in the first place, there will be the negative 1. Okay? So in this case, now I constructed, if I remove one node, what is the remaining height? Okay? So if I remove, okay, I'll just do a very quick one. If I remove B, what's the height now? 3. That is very fast, right? You can now determine very fast, right? You don't have to count anymore. So at first, I will need to spend this much time to construct this tree. But once I constructed, right, if I want to get the B, from the root, I just need to go to B, I return the value. What's the runtime for that? Just for the query part? Not O1. Not O1? O log n, because this is a height balance tree, okay? So we will take O log n time. So now the tree is complete. If I want to remove D, I'll find D, I return the value as 3. That's it. Easy? Easy. Okay? So the runtime here is the time to pre-process plus the time to query. Pre-processing is quite long, so if to traverse the nodes, that will take the ON time. But why do we need to take the ON? Because instead of doing the height every time, just need to calculate it once. Then once we calculate this, we can just directly query it. Okay? So we can query it in m log n time. Okay. Wait, I think the pre-processing part should be n log n. I think I did something wrong here. So in total, that will give us the m log n plus n. Sorry, I'll fix this later. Okay? Any questions so far? No? Okay. If no questions, then I think today we are on time. Yes, finally. So that will be it for today's tutorial. All the best for your midterms and have a nice recess week, guys. Okay? Chill yourself out, okay? If you want to grind, PS5 is out, so you can try to do PS5 also. Okay? But that will be it for today's tutorial. If you have any questions, I'll be here until 6. Okay? Nice, today's on time. I'm so happy.